look forward to listening to his lecture about the dark side of the universe. Let me tell you a little bit about Kazuya. He moved to the UK from Japan, where he was awarded his PhD from Kyoto University in 2002. And he first came to our university in 2004, supported by a Japanese fellowship, which was only originally meant for a year. So there were people with a great deal of foresight who saw his brilliance and made sure that he never left. And of course, since worked his way through the ranks, including becoming professor of cosmology in September of last year. Kazuya's research interests lie mainly in theoretical cosmology, which involves studying the origin of structure in our universe. He's interested also in explaining the late-time acceleration of the universe by modifying general relativity on cosmological scales and developing cosmological tests of gravity. Kazuya, as I said, has achieved great accolades during his academic career, including winning the Philip Liverpool Prize in 2009 and an RC UK Academic Fellowship in 2006 to 2011. He's also a PR, Principal Investigator of the Royal Society International Joint Project with the Tower Institute at Kyoto. The collaboration between Kyoto and Portsmouth was awarded the Daiwa Adrian Prize in 2010. In addition, in the same year, he won the Young Scientist Award of the Physical Society of Japan. I know that Kazuya still has deep links with Japan, and I know that he would like us to thank his supervisors, mentors, and collaborators in Japan who are not able to attend tonight, but they continue to support. And as we're waiting, I would say a lot of his colleagues from around the UK are here today, so I know he wants us to thank them in particular. But to thank all of you for being here this evening. But Kazuya, this evening is an important event for you personally, for your family, and for the university. And we're very much looking forward to hearing your story and learning more about your research. It gives me great pleasure to invite you to present your professorial inaugural lecture.
I'd like to discuss about the dark side of the universe. And this is basically our journey to understand gravity from Newton to Einstein and beyond. So what is gravity? So Newton thought that gravity is an invisible attraction between any object with mass. And using this very simple formula, he could explain everything from the motion of object like this pointer in this room to the motion of planet in the solar system. But Einstein challenged this conventional idea of gravity, so let's follow his thought on gravity. And Einstein often used this thought experiment, so just use your head and understand physics. So let's imagine that you step in the lift and the lift goes up. So how do you feel? Do you feel your weight becomes heavier or lighter? Yeah. So in this case, you want to stay here, but the lift goes up, so you think that there is some force acting on you downward, so you think that your weight becomes heavier. On the other hand, if you step in the lift and the lift goes down, in this case, you feel that your weight becomes lighter. Okay. So next time, if you have a chance to use lift, please try this. And I do not recommend for you to do this, especially for our students. If you cut the cable of this lift, so what happens? So in this case, basically the lift is falling down and you are falling down. So in this case, you do not feel any gravity at all. So this means that you can mimic gravity just by having this acceleration. So acceleration means that the velocity is changing. For example, in this case, you start from zero velocity, and velocity becomes larger and larger in this case, and this is the acceleration. So you can mimic gravity just by acceleration. And this also says that gravity depends on how you observe it. So let's imagine that you are in a free falling lift, And if you have an object, this is falling down, but you are also falling down, so it looks like this is floating without gravity. So in fact, you cannot distinguish between this situation and this situation where you are in space. So if you cannot see outside, you may think that you are in space. However, of course, if someone is looking at you from outside, this person says to you that in fact you are falling down because of the Earth's gravity. And eventually you will notice because you will hit the ground. But this means that in fact you can even make gravity disappear, you just need to free fall. And then you can make gravity disappear. So it seems gravity is not like invisible force acting on this object, and this depends on how you observe. So the next question is, so how you sense gravity then? So if you can make gravity disappear, so how you sense gravity? So in this case, you have to have a very big lift. In fact, you have to have a lift whose size is the size of the Earth. You cannot build this, but in your head, it's very easy to think about this very large. So let's say you are free falling inside this lift. And you have a ball, and it looks like this ball is floating for you because you are also falling down. So you can make gravity disappear for this ball. But however, if you have two balls, and these two balls are attracted to the center of the Earth, in fact, they are not falling down in this way, they are falling down in this way. So this means that if you look at these two balls, because you are falling down together, you don't see this motion downward, but it looks like these two balls are attracted with each other. Hopefully you can see from this animation, you can see that there is some kind of attraction between these two balls. And this is known as the tidal force, and it's the same mechanism to have a tide due to the moon's gravity. And you cannot eliminate this force between two balls. So that's the observation. So you can make gravity disappear if you look at just one ball. So it means that you can make gravity disappear in a small part of the space. But if you have two balls separated at the distance which is comparable to the size of the Earth, which is creating gravity, you cannot eliminate gravity. So that's the property of the gravity. The next step is to come up with some mathematical way to express this nature of gravity. And this is what Einstein used. So this is a ball or sphere. And in fact, the Earth is a very good example. So we are living on this sphere, Earth. But in this room, we do not feel any curvature of the sphere. So we think that we are living in a flat space. Okay? And in fact, in flat space, if you have two parallel lines, they never intersect. However, we know that we are living on a sphere. So if you travel long enough, you notice that these two parallel lines will converge. And in this case, you arrive at the sphere. But in order to see this curvature of the sphere, you have to travel for a long time. So this looks very familiar because the effect of this curvature of the sphere you can ignore in the local part of space, like in this room. However, you cannot ignore the curvature of this object if you travel long enough. So this is pretty much like gravity. So you can make gravity disappear in the local part of space, but you cannot make gravity completely disappear in the extended region of the space. So using this analogy, Einstein came up with this idea of gravity. So according to Einstein, in fact, gravity is created by this curvature of space and time. So I will come back to this time part later. So the sun creates this curvature of the space. So John Wheeler said that the matter tells space-time how to curve. So let's imagine that the sun creates this curvature of space, and in turn, this space-time tells objects how to move, like stars and the comet, planet, and comet move because of the curvature of this space-time due to the sun. So basically, space-time tells matter how to move. So the next question is how space-time tells matter to move. So let's coming back to this analogy. So let's say you have a flat plane, and if there is no force, the object moves from A to B along a straight line. So what is special about this straight line between A and B? So the special point about the straight line between A and B is that this is the shortest path you can take. So if we want to go from here to here, the shortest path is a straight line. So let's imagine that our Earth is flat, and if you want to go from Europe to US, this is the path you want to take. However, we know that Earth has curvature, and in fact it's a sphere. So if you want to go from Europe to US, you have to take this route. So this is the shortest path, and in fact you have to go through Europe. And then Newton says that the trajectory of this object is changed because of gravity. So this is a Newton point of view. But Einstein says that the object moves along this path because this is the shortest path in this curved space-time. So this is the way how space-time tells matter to move. So matter just tries to follow the shortest path in this curved space-time. So Einstein came up with this very elegant way of understanding gravity. So at this point, it's just an alternative way, a different way of looking at gravity. But then Einstein found that this theory can predict many interesting predictions. And one prediction is that gravity even bends light. So we believe that the light is made of photons, and photons have no mass. So according to Newton, photons shouldn't feel any gravity. But let's come back to this experiment using a lift. So you are in a lift, and someone shed light from side. So let's say you have a transparent wall, and then you goes up, so the lift goes up with some acceleration, so the velocity becomes larger and larger. So for you, you have a light, and you goes up, so it looks like this light goes down, because you are moving up. Okay? And you are moving up with increased speed, so this means that this light goes down, but faster and faster. So for you, it looks like this light is going down along this curved trajectory. Okay. And I said that if you have an acceleration, so if you go up, you feel gravity. And in fact, you cannot distinguish between having acceleration and gravity. So this means that, in fact, it looks like gravity is changing the path of light. So this is the prediction you can easily understand from this analogy. And you can understand this as the effect of the curvature of space-time. So let's say the sun creates this curvature of space-time. And you have a star, and the light comes in this way, but here, because space-time is curved, the light is deflected and comes to us. So it means that even if the star is here, it looks like the star appears in this position. So this means that due to sun's gravity, there is a deflection of light, and the position of star is moved. And using Einstein's theory of gravity, you can precisely predict this angle, deflection angle. And this was tested, in fact, in 1919, on this very particular day, May 29th, by Eddington. The idea is very simple. So you want to measure the position of stars when the sun is here. And you again measure the position of stars when the sun is elsewhere. And then compare the position of these stars. And in this case, because of the gravity of the sun, the light is deflected, and the positions of these stars are slightly different. But of course, there is one problem. You cannot observe stars if the sun is here. So that's the reason why this particular day is important, because this was the day before I did. So the moon hides the sun. So you could observe stars even if the sun is here. Then he measures the change of the positions of these stars and compared with Einstein's prediction. And then he found that indeed these changes were exactly what Einstein predicted. And this is the news in New York Times at that time. And this shows the excitement of the people at that time. So it says Einstein's theory triumphs. Stars not where they seemed or were calculated to be, but nobody did work. So this shows the excitement of usual people. And in fact, Einstein's theory is a very difficult theory, and only a few people understood it. But this magical theory can predict the change of star positions due to sun's gravity in a very high. However, this is not the end of the story. Einstein's gravity then further predicts a very weird thing about time. And in fact, even gravity changes time. So let's think about two clocks on the ground, so in England, and another clock in Highland in Scotland. And in Highland, because you are on the top of mountain, the gravity is weaker, because the distance to the center of the Earth is longer, so the gravity is weaker. And according to Einstein, gravity even changes time. And in fact, stronger gravity means that time ticks slowly. On the other hand, if you have a weaker gravity in Highland, in fact, time ticks faster. So that may be the reason why Scottish people are a bit different from English people, and they're a bit advanced. And in fact, this change is tiny, so you wouldn't notice it. However, this becomes very important if you want to send a signal from the Saturn to the Earth. And this happened when the Cassini satellite went to the Saturn, and it sent the signal to the Earth. And this is very similar to the Eddington's experiment. So it sends signal when the sun is here. So due to the sun's gravity, time ticks slowly around here. And then it compares the timing of the signal when it sends the signal when the sun is not here. And there is a time delay if the sun is here. And this time delay you can compute using Einstein's theory of gravity. And again, this has been confirmed by this study. And in fact, this is the strongest confirmation of Einstein's theory of gravity today. So I hope that I'm starting to convince you that Einstein's theory of gravity is right. And in fact, you are using it in everyday life. So I think you use GPS in everyday life. And GPS works because you synchronize clocks on the satellite and clocks on this ground, and then you try to find out the position of your place. But important thing is that you have to synchronize your clocks. But remember that in Highland, because of the height, gravity is weaker. So this means that the time ticks faster. But this effect is much larger because you have a satellite orbiting around the high Earth. And in fact, the time ticks faster on this satellite by this amount per day. So this is a very, very small number. So that's the reason why Scottish people are in them not that different. However, this small difference is very important if you want to get GPS working. Because to get the accuracy of 5 to 10 meters using your GPS, you have to synchronize these two clocks by this accuracy. And this number is much, much smaller than the effect of gravity according to Einstein. So this means that if you do not take into account this time delay, well, in this case, time ticks faster on this satellite, basically your GPS doesn't work. And in fact, if you ignore Einstein's gravity's effect, the errors in GPS accumulate like 10 kilometers per day. So if you do not trust Einstein's theory, do not follow your signal, because you end up in a very So you have to trust Einstein's gravity, and I hope I convinced you that the Einstein's theory of gravity does not only give a very elegant view of gravity, but also it has been tested many times by many means, and we do trust his theory of gravity. So then it makes sense to use his theory of gravity to understand our universe. So this is the subject of cosmology. In cosmology, we are trying to understand the universe as a whole, and probably this is the oldest science in human history. So we try to come up with a picture of our universe since the beginning of human history, and we have been improving our picture of the universe. And in fact, Einstein's theory of gravity revolutionized our view of the universe. But there is one problem. So the Einstein theory gives Einstein's equations, and you have to solve these equations to find out the solution for your universe. But however, Einstein's equations are so difficult, so even after 100 years, we don't really know huge solutions to these equations. So we need to simplify our space-time to get some solutions from his equations. And this is our assumption, so this is homological principle. So this principle says that there is no special point in our universe. So this is our belief, but we trust this principle. So we want to come up with a space which satisfies this principle and try to find solutions to the Einstein equations. The problem is that it's very difficult to imagine three-dimensional space. So we are living in a three-dimensional space, but I cannot draw three-dimensional space from this two-dimensional screen. So I will use this lower dimensional analogy. So from now on, you are an ant living on this plane. Okay, you are not a human, so you are an ant living on this two-dimensional plane. Okay, you cannot jump, so this is your universe. So this is a representation of our universe, and you cannot escape from your universe, so you cannot move up here. So you shouldn't ask outside this plane, because this is your universe. Okay. So now you think about this, and this universe is not a very good universe because there is a center and there is an edge. So this does not satisfy this principle. So we have to come up with some two-dimensional plane or membrane which satisfies this assumption. And again, sphere gives the answer. So let's imagine a sphere. And you are living on this surface of the sphere. So you are an ant living on this surface. Okay. The special point about this sphere is that there is no special point on the surface of the sphere. So every point on this sphere is equal. So there is no edge, there is no center. So this is a very good representation of our universe. So this is our universe. So this is you. So you are living on this surface of the sphere. And let's imagine that now this surface of a sphere expands. So let's imagine that you have a balloon, and the surface of this balloon is your universe. And this balloon expands, and then your universe expands. So let's say we have galaxies made of many stars, and this is our galaxy. And try this again. And this balloon expands, and then universe expands, and all the galaxies are moving away from us. So this is a prediction of expanding universe. And the good thing about this is that this may be our universe, our galaxy, but this may be our galaxy. But each galaxy on this surface see exactly the same expansion because there is no special point on this sphere. So this satisfies the cosmological principle. So this is the view of the expanding universe. So basically, you are living on the surface of the balloon, and once this balloon expands, your universe expands, and galaxies are moving away from you. And this can be represented by the radius of this balloon. So this is a function of time, so this depends on time. And if this radius balloon becomes larger and larger, the universe expands. And this h is the gradient of this curve, so this is the expansion rate. So this tells you how fast this balloon is expanding. And Einstein's equation gives the relation between expansion rate and energy density of matter living in this universe. So this is the Einstein's equations. So basically, expansion rate, so that how fast universe expands, is determined by energy density of matter in the universe. And once the universe expands, all the galaxies are moving away from us, and the velocity of these galaxies are determined by this expansion rate and the distance. And this is known as the Hubble law, and this is a prediction of the expanding universe. And this was confirmed in 1929 by Hubble. So he measured the distance to the galaxies, and he measured the velocities of galaxies, and he noticed that, in fact, the velocities of galaxies are getting higher if the distance is longer. And his measurements were not very precise, but you can see that these data points can be fit by a straight line. So this means that the galaxies are not randomly moving away from you. Galaxies are moving away from you because the universe itself is expanding. So this is the evidence that our universe is expanding. And after 80 years, we have been improving this measurement. And in fact, we completely trust that our universe is expanding. However, Einstein disliked this idea. And it's very interesting that even Einstein couldn't escape from conventional idea at that time. Because 100 years ago, many people believed that the universe must be static. So static means that the universe shouldn't expand. That was just a belief, but Einstein even couldn't escape from it. And he had a problem, because every time he solved his equations, he gets this expanding universe. So he wanted to have this static universe. Static means that the expansion rate is zero, so meaning that the universe does not expand, so stay the same. To achieve this, he introduced this constant, and it is an alpha cosmological constant represented by this Greek letter lambda. By having this constant, he found the solution that h is zero, so the universe is static. And he was very happy. But then, 1929, Hubble confirmed the Hubble's law, so the universe is expanding. And later, Einstein finally abandoned this idea of static universe. And he said that, in fact, this was his biggest blunder. Instead, to introduce this constant just to get static universe. Because he basically destroyed his beautiful theory by adding this constant just to have static universe. But however, after 70 years, this cosmological constant is coming back. So let's come back to Einstein's equation. So this is the equation of the universe. It's very simple. You just remember this equation. The expansion rate, so how fast the universe expands, is determined by matter and cosmological constant. If I can do one mass in my lecture, I want to divide this equation by h squared. So this becomes 1, and this becomes capital M, and lambda divided by h squared becomes capital C. This is the Einstein's equation applied to our universe. It's very simple. The meaning of this equation is that if this M is 1, there is enough matter in our universe to explain the expansion of the universe. If M is not 1, you need something else, like cosmology. So basically, cosmology is finding out what kind of matter we have to explain the expansion of the universe. And then people already noticed something was wrong, even in 1930s. So they started to count the ordinary matter, like galaxies and stars and gas, and they counted all the energy density, and they found that they only give 5% of the energy that is needed to explain the expansion of the universe. So in terms of this M, it only gives 0.05. So we don't have enough matter to explain the expansion of the universe. There must be something else. We don't know what it is, we just call it dark matter, because we don't see it. And this dark matter does not interact with ordinary matter like photons. Even if you have dark matter particles in this room, they just pass through you, so you don't see it. And we believe that our galaxies made of visible stars are surrounded by these dark matter particles. Then, of course, you will ask how you believe there is something you cannot see. And in fact, Einstein's theory of gravity helps here. And in fact, you can see, in some sense, what you cannot see. So this is the idea. So this is very similar to the Eddington's experiment. So let's say a galaxy, which is made of billions of stars, and we have a star. And this galaxy has a gravity, so this means that this distorts the space-time. So this deflects the light. So it looks like if you have a galaxy, and then if you look at this star, it looks like you look at the star through a lens. And this is a picture of this one star, but you see many images because this galaxy, the gravity of this galaxy acts like a lens, this reflects the light, so that you see this beautiful image. But this is just one star, but you look through gravity of this galaxy, then you see these images. And the thing is that this deflection of light is determined by gravity, so this is determined by how much mass you have. And it doesn't matter, it is made of ordinary matter like galaxy and stars. In fact, that matter also deflects light. So in this way, you can infer the existence of matter which you cannot see through the light. And using this technique, now we believe that the dark matter gives the contribution to the matter like 25%. So this means that, in fact, there is 5 times more dark matter than ordinary matter. However, this is still not enough, because we only have 5% of ordinary matter. We have 25% of dark matter, so we still need 70%. So the last possibility is the cosmological constant. So what is cosmological constant? So the question is, what is constant? So let's imagine that you have 3 particles in this box. This box will expand, and then the density of this particle decreases, because the number of the particle remains the same, but the volume increases, so the density decreases. And this is what ordinary matter does. So once the universe expands, the density of matter decreases. But this cosmological constant has constant density, meaning that if the volume expands, you want to keep the same density. So in this example, you have to create more particles to keep the same density. So this means that energy increases if the volume increases. So this is a prediction of this real cosmological constant. And if you have this cosmological constant in your universe becomes crazy. Because basically the universe wants to expand more and more because you gain energy by expanding more. So if you have this cosmological constant, so coming back to this expanding balloon, the radius of this balloon behaves like this, so this is time, and in fact the expansion of this balloon becomes faster and faster if there is a cosmological constant. So this is a prediction of the cosmological constant. So if you have a cosmological constant, the expansion of the universe accelerates, meaning that the expansion becomes faster and faster. So how do you test the existence of the cosmological constant? So we can use this supernova. So supernova is a very bright star. In fact, this is an explosion of the star at the end of its life. This is one star exploding, and this is as bright as a galaxy which is made of billion stars. So this means that you can observe this supernova to a greater distance. So how we test the existence of cosmological constant using this supernova? The idea is very simple. So let's consider 2 universes, one without cosmological constant and one with cosmological constant. So the effect of the cosmological constant is that the expansion of the universe becomes faster and faster, meaning that the distance to this supernova becomes longer compared with the universe without cosmological constant. And if the distance becomes longer, this supernova looks dimmer. Okay? So that's the prediction. If you have a cosmological constant, the universe wants to expand faster and faster, and the distance to the supernova becomes longer, and they look dimmer. And this prediction was tested by measuring the distance to the supernovae and measure the brightness. And this is using a funny unit, so the supernovae become dimmer in this direction. And this is the prediction of the universe without cosmological constant. And this is a prediction of the universe with cosmological constant, where cosmological constant is giving 70% contribution to the expansion. And these are the data points, measurement from supernovae, and they are consistent with the universe with cosmological constant. So everything will look dimmer compared with the universe without cosmological constant. So this means that the expansion of the universe, in fact, is accelerating. And we seem to have 70% of the cosmological constant, which is contributing to the expansion of the universe. And this was the breakthrough of science in 1998. And in fact, in 2011, Nobel Prize in Physics was awarded to this discovery of the accelerated expansion of the universe. But we have to be careful. I mean, the Nobel Prize was not awarded to the discovery of the cosmological constant. So the Nobel Prize was awarded to the discovery of accelerating expansion of the universe. The reason is that we have no idea what this cosmological constant is. That's the reason why we just name it dark energy, but we have no idea what this energy is. So basically, this is the dark side of the universe. So I said that Einstein's theory is giving a very convincing result in the solar system, and you are using it in everyday life. But somehow, if we apply this theory of gravity to our universe, the picture is looking a little bit strange. Basically, we only know the 5% of the energy in the universe, which is made of usual galaxies and stars. We have 25% of energy made by dark matter, and we have 70% of energy made of this mysterious dark energy, which makes the expansion of the universe faster and faster. So it seems something is wrong, because we only know 5% of the matter in our universe. But then I said that, well, maybe this is just cosmological constant. After all, Einstein introduced this cosmological constant. So what is the problem of this cosmological constant? And in fact, even better, we can predict this cosmological constant from well-tested physics. For example, I can use physics describing electrons, and we know electrons exist. We know very well what is the physics describing electrons. And we can compute the cosmological constant from this theory. And this is the answer. So this is what you get from electrons. The electrons predict this cosmological constant, which is this number times the cosmological constant you need to explain this accelerated expansion of the universe. So what is wrong? It's completely wrong. And the problem is that we have no idea why this is wrong, because we use a very well-tested theory to predict this. We used very well-tested Einstein theory of gravity to measure the cosmological constant from universe expansion. They don't match at all. And I don't have any answer. So I haven't given you the answer today. And in fact, maybe this is the most famous quote by a new theoretical physicist. So this is the most embarrassing observation in physics. That's the only quick thing I can say about energy. That was true. So maybe I do not have enough time left in my life to solve this problem. I see a lot of young people in this room, and you can solve this problem. This is the exciting thing. This is the most important problem in theoretical physics. We don't know the answer. So this is so fundamental, I think we probably need some radical ideas. And this happened, in fact, at the beginning of the last century. So in the beginning of last century, people observed the orbit of Mercury, and perihelion is the closest point to the Sun. And this perihelion of Mercury changes according to the orbit. And people couldn't explain this using Newtonian gravity. And people are very puzzled. And a French mathematician introduced a dark planet near the Sun called Vulcan. And this gravity of the Balkan changes this perihelion. And his mathematical model is very precise. He could explain all this in a very accurate way. But there was only one problem. We couldn't find the Balkan. The Balkan was never found. And in fact, for this, I know the answer. The answer was we had to improve our understanding of gravity. In fact, this is another confirmation of Einstein's gravity. So using Einstein's theory of gravity, we can explain this shift of perihelion in matter. So maybe the similar thing is happening today. The Balkan, so dark energy is kind of Balkan, so we introduced it to explain this accelerated expansion of the universe, but we don't know what it is. Maybe we have to improve our understanding of gravity again to explain it. So that's the radical idea I'm interested in. And this is one of my favorite ideas to go beyond Einstein. So let's come back to this picture. So you are living on the surface of this sphere. So you are the arm. I said many times, you cannot escape from your universe. So you cannot jump. You shouldn't ask what is outside your universe. But what if there is some extra space outside our universe? So we call this extra dimension. But you don't notice this extra dimension because you are confined to this surface. So you cannot see these extra dimensions. However, gravity is different. As I said, the space-time tells how matter moves. So the sphere, the shortest path is this. But if there is extra space, in fact, the shortest path may be like this. So even if you cannot see extra dimensions because you cannot jump into the extra dimensions, you see this change of gravity. And this change of gravity may be causing the acceleration of the universe. So this is one possibility to go beyond Einstein. And in fact, this is precisely what I studied during my PhD. And so I did my PhD at Kyoto University and took my PhD in 2002. And this picture is called brain world. So this brain is not our brain. So this is membrane. So this is basically a piece of paper. So we are living in a piece of paper in extra dimensions. And this is known as the brain world cosmology. And this was the title of my thesis. In fact, I graduated from a School of Human and Environmental Studies, but this has nothing to do with human and environment. Maybe I spelled brain, and I didn't notice it. And then I moved on to the research fellow supported by the Japanese government. I took my research fellow at the University of Tokyo. And at that time, the Institute of Cosmology and Gravitation here at Portsmouth was the world-leading institute studying this brain world gravity. So that's the reason why I decided to spend the final year of this research fellowship here at Portsmouth. And in fact, this is the end of my very brief history because I'm here since then. And so I have been here for 12 years. And this was my best decision in my career. So I wrote academic articles summarizing the development of this brain world gravity with Professor Roy Martens. And also I keep a very good connection with community in Japan. And in fact, Paul already mentioned that we had this award, the collaboration between Portsmouth, led by Professor David Wongs, and the Kyoto University, the Yukawa Institute for Theoretical Physics, led by Professor Amisawa Sasaki, was awarded this AAM prize. And Professor Sasaki came to here and attended a ceremony. And you may notice that I am missing in this photo. And in fact, on that day, there was heavy snow. And I was stuck on the train for many hours and I gave up. And after 12 years living in the UK, of course I know I can't be stuck on the train. Anyway, so how we test this idea? So we first need to come up with the idea where the relation between space-time and matter is different from Einstein. Because we don't want to have this cosmological constant or dark energy to explain this crazy expanding of the universe. For example, this brain word gravity gives this possibility. So we are living on this piece of paper, we have extra space, and we get this completely empty gravity. And in fact, the first three terms in this equation is Einstein's equation. So this is the Einstein equation. So this G represents space-time, T represents matter, and you have lambda. But you don't want to have lambda. But if you have extra space, you get all these exciting terms. So these are the most important equations in my presentation. And then this gives the possibility that without having lambda, you could explain the accelerated expansion of the universe. But then, basically, I worked on this kind of theories when I started my study. But then, after coming to Cosmos, I started to think, so how we can test this complicated theory. So basically, we want to simulate our universe. And basically, we have a lot of dark matter particles. So basically, our universe is mainly made of dark matter particles. So let's start again. So dark matter particles have initially nearly homogeneous distributions. A good thing about dark matter is that it only feels gravity. So you make this very interesting pattern of dark matter particles just due to gravity. So this is a very good way to test your gravity, because if you change gravity, you change the distribution of dark matter in your universe. And in fact, this is the universe described by Einstein's theory of gravity with cosmological constant. And this is the universe described by one of the gravity theory, which is different from Einstein's gravity. And you need a supercomputer to do these simulations. So these simulations are done by Botar, a research fellow here at Portsmouth, and we are using the supercomputer here at Portsmouth, and we can create a detailed distribution of that matter given gravity. And you should be able to tell the difference because they have different gravity. And it's very difficult to see, but just look at these two objects. So basically, they are the collections of many dark matter particles, which we call dark matter halo. And in this universe, these two dark matter halos are separated. But in this universe, you see that these two dark matter halos are already merged. So you see the difference, and this is because the gravity is a little bit stronger in this universe. So you see this merging of these two dark matter halos earlier than this universe. So this is what you can project. So if you change gravity, you change the distribution of dark matter, and then you want to compare this with the distribution of galaxies you can see. So this is the map of the galaxies we observe. So this is not simulation. This is what we observe. So this shows millions of galaxies and shows the distribution of galaxies. And this was done by Sloan Digital Sky Survey. Again, Cosmos played a very important role to create this map. And you see that this distribution of galaxies is very similar to the distribution of dark matter. And in fact, we believe that galaxies are formed inside these dark matter halos, and we can see these galaxies, and they follow the distribution of dark matter. So this means that you can compare your predictions of the distribution of dark matter, which depends on your gravitational theory, against the observed galaxy distributions. You can test your gravity. But to do that, you need a very advanced statistical method because the difference is usually small. Also, you need to understand how galaxies are formed inside these dark matter halos. And this is a very important problem. So in May, Professor Daniel Thomas will give another lecture. He will talk about how you make galaxies inside these dark matter halos. And then, of course, we have to understand how these observations are made. But we have a very exciting time ahead because we will have a very good data. For example, in 2020, a Euclid satellite will be launched. So this is the European Space Agency mission, and try to measure the position of galaxies and create this kind of map, but much larger volume and precise one. So using the data from this mission, we can test the theory of gravity. And this is a huge European mission, including 1,000 scientists, and we are the Institute of Cosmology and Gravitation, is an important part of this mission. So I started talk about the test of Einstein gravity. So I didn't test it using this deflection of light. The Cassini satellite confirmed this prediction, and you are using it every day in GPS. But we are getting more exciting ways to confirm Einstein's theory of gravity. Last year we had a very interesting news. So we detected these gravitational waves. So this is caused by the colliding two black holes. And this creates the oscillations of space-time itself. And we detected these oscillations. This will give additional test of Einstein's gravity. And in the next 5–10 years, we can use cosmological observations to test Einstein's theory of gravity. So this is a summary of my talk. So I hope I convinced you that the late-time acceleration of the expansion of the universe is one of the most fundamental problems in theoretical physics. So in the next 5–10 years, I try to develop a cosmological test of gravity and try to seek solutions to this accelerated expansion of the universe by challenging the conventional Einstein gravity. So I summarize research development again in this review article last year. And I'm pleased that my research has been supported by European Research Council since 2008, and this grant will support my research until 2020. So of course we know the UK will leave EU, but I hope we are still in European and international collaborations. And in fact, I hope this country will remain open to this blue sky research. And finally, of course, I couldn't achieve all this without support from my family, my mentors and collaborators in Japan who couldn't be here. And of course, I'm very grateful to my students and postdocs in this room, and of course, my colleagues in ICG and the university. And finally, I would like to thank everyone in this room for coming to my lecture.
Kazuya has presented today is just an example of some of the excellent research that goes on in the Institute. So, I think I'd like to start by saying Professor Kazuya Koyama, and I think on behalf of everybody attending here today, I'd like to thank you for your lecture, for your insights. And I'm starting to understand now the complicated equation that you have to deal with. So I think that's good to know. And thrilled really to have Kazuya as part of the faculty because I think his contribution is noted, and I think he has been very humble in not really listing every single thing that he has done. And I have to say that he's one of our most productive researchers that we have in the Institute. So I think it's well deserved that the university now has acknowledged his contribution by conferring the title of professor. And I think we are looking forward to your continued work in this, and hopefully you'll find the answers to some of these difficult questions that you're asking yourself. So to finish off, I think there is some drinks that you are invited to join us later on. But before I close this session, I'd like to thank everybody who has attended today. I'd also like to thank the organizers of this event, because sometimes we forget that there's a lot of work that goes behind the scene in organizing some of these special events that we run in the university. But particularly, I would like you to join me in thanking Professor Kazuya Koyama for a fantastic lecture and wishing him well for the future. So please join us on stage.
Yeah.